Okay, let's do module 2. This will be about gates and about quantum adder at the end. So to begin, there are classical bits, which there are classical logic gates for. We have inverter, so for a bit 1 it becomes a 0, for a bit 0 it becomes a 1, it just flips it. And for an AND gate in the classical domain, you have, if it's 0 and 1, that becomes 0. It just has to be 1 and 1, and then it become a 1, right? One thing about these gates is they usually are not reversible. So when you do an AND operation in the classical domain, you cannot recover given B0 or given B2, the result. You can't uncover what B0 and B1 can be just from B2. Obviously, B2 is 1, then you know both are 1, but if this is 0, you don't know what B0 and B1 are at any point. Okay, and moving on to quantum gates. So the difference between the two, for logic gates, we just discussed the main difference. One is they only run forward, or not they only run forward all the time, but some of them only run forward and you can't recover information. With quantum gates, they are always reversible, and you can always uncover and unravel the steps to get back the original states and bit positions of everything. So one more requirement for quantum gates is that they are unitary matrices. So these gate operations can be captured in a matrix. And when they are captured in a matrix, applying the Hermitian conjugate transpose, I don't remember exactly what the term is, but this is the symbol. You take the complex conjugate of all the entries, and then you take the transpose and you multiply it with the original matrix, and you'll get back the identity matrix always for all quantum gates, which is how they're reversible. So yeah, so that's right. And so, for example, one quantum gate is I want to do one with an imaginary number. I think this is the poly y gate, which flips around the y axis. So this gate, if you multiply by its conjugate transpose, first let's figure out what that is. So first we take the conjugate. The conjugate means for every complex entry, a plus bi, you just flip this sign, whatever it is. So if it was 3 plus 9i, the conjugate is 3 minus 9i. And if it was minus 6i, it becomes a positive 6i. So all you do is just flip the sign of the coefficient in front of the I term. You don't touch the other one ever. So let's get rid of that. So here it would be 0. We don't touch that because it's all real. The complex component, this can be written as 0 plus minus 1 times I. So it's just 1 times I. So this is just an I. And this will be a minus I. And then this will be a 0. And then we have to take the transpose. So we have 0. Now we have an I at the bottom. We have a minus I at the top and a 0. So what I did was I moved this top element, I kept in place, and I pivoted this down here, and then I moved that up there. That's how you take the transpose. So now this is the Hermitian transpose of this original matrix, or of this original matrix right here. So if I multiply the two, I should get back the identity matrix, and then we know it's a valid quantum gate. So 0 minus I, 0, 0 minus I, 0. You multiply these two, you get minus I squared, and that's from this times this plus this times this. Then we're going to do this dot product with that, so you get 0. We can do this dot product with that, so we get 0. We do this dot product with that, and we get minus I squared again. And I is equal to square root of negative 1, so I squared is negative 1, and negative times negative 1 is 1, so you just get the identity matrix from that. So that is a property of all unitary matrices, that U conjugate transpose times U is equal to I in any order. Okay, like you could do U times U conjugate transpose as well, and you'll get I as well. So that's how you can confirm a matrix is unitary. If it is unitary, then it is a valid quantum gate. So if you're trying to see if a gate is possible and it's not unitary, you instantly know it's not correct. So that's the definition of unitary, just that if you multiply by its conjugate transpose, you get the identity matrix back. Okay. And yeah, we talked about it's reversible. That's the main requirement, and that's rooted in the fact that it is unitary. Okay, so the first gate we're going to talk about is the X gate. X gate, and these are called the poly gates as well. They're the same thing. It doesn't really matter. I'm just going to call it X gate here. What it does is it flips a qubit into the opposite state and ignores the sign here if you're starting at 0 and 1. So in our block sphere representation, just pretend that's the origin connecting all the points. If we start at position 0 right here, an X gate operation will flip it like this until actually it flips it the other way. Okay, let me explain what X gate really does first of all. So X gate rotates by pi around the X axis, and you have to first visualize a perpendicular plane to the other two axes. So for Z and Y, a perpendicular plane would look like, is this a good idea? No, that's not a good idea. A perpendicular plane would look like that, right? Going on Z and Y. And I can try drawing a square outline too, if that helps. So you can really see exactly what plane that is. And now we take the x-axis and we rotate around it this way, which is clockwise to us, but if you orient the blocks for otherwise, it's a counterclockwise rotation as it's supposed to be. But in this representation, it rotates by pi around the x-axis like so. And the X gate will take a bit from ket 0 to ket 1, and the same way it'll take a qubit from ket 1 to ket 0. So that's the X gate. That's like visually what it does in the block sphere, and it swaps the amplitudes of each of the qubits for ket 0 and ket 1. So the matrix for this is a 0, 1, 1, 0. We know this is unitary because if you multiply by its conjugate transpose, which is actually the exact same matrix, then it's the inverse. And you can see like 0, 1 times 0, 1 here would be 1 on the very first entry and so on. It would be the identity matrix. Okay, so how to think about this is, or how to think about the utility of the matrix in this whole like quantum representation is, it's important to grasp what the vector actually means. And the vector is the basis vector and how much amplitude is in each of these basis vectors. So for a 1 qubit system, the basis vector is written as alpha 0 ket 0 plus alpha 1 ket 1, right? So this entry right here would be alpha 0, this entry right here would be alpha 1, and when you multiply by this unitary matrix, which is the X gate, then you get alpha 1, alpha 0. It flips the probability amplitudes of each of these basis states. And that is exactly what's going on here. If you started at bit 0, or let me do this in a different color. If you started at qubit 0 and you turned it into a 1 using the X gate, what's really happening is you have alpha 0 is equal to 1 times ket 0 plus alpha 1 is equal to 0 times ket 1. And that simplifies to just ket 0, right? And that's what we're saying we're starting with. And then when you apply this matrix X, you are flipping the probability amplitudes. So alpha 0 becomes alpha 1 becomes alpha 0. So now you have 0 times ket 0 plus 1 times ket 1, and that's equal to ket 1. So that's kind of like Y, and it ties up the physical geometric representation with the matrix representation. Okay. But it doesn't stop there. So for multiple qubits, and I'm getting a little ahead of myself, but I do want to show how to think about it there. for multiple qubit systems, let's say the matrix is this. Let's just say it's the identity matrix. So this will not do anything to any of the probability amplitudes. The way to think about the vector entries here is, again, the phase amplitudes, or the probability amplitudes of the basis vectors. So now instead of 0 and 1, the basis vectors are 0, 0. It'll be alpha 0, 0, 0, alpha 1, 0, 1, plus alpha 2, 1, 0, plus alpha 3, 1, 1. So that's the way to think about it. And you can see from the effect of the matrix, depending on what the matrix is, if it's not identity matrix, you can see how these phase amplitudes change, and then you can like infer what's going on there. So for example, if I gave you this matrix 1 0 0 0 0 1 0 0 0 0 0 1 0 0 1 0. So this is essentially the identity matrix, but the bottom right corner is flipped into an X gate. So kind of looking at this matrix, you can kind of estimate what it might be, in that an X gate is applied and then the other qubit system is not changed. Hint, or I'll just say, I guess, C naught, but let's say we didn't know it was C naught and we applied this product on the probability amplitudes of these basis vectors, then we'll get the results alpha 0, alpha 1, alpha 3, and alpha 2. Right? These two entries will be swapped. And then if you break it down into this representation right here, you'll see it is the alpha 0 basis vector is the same, the alpha 1 basis vector is the same, and now alpha 3 times 1 0, or if we keep the coefficients in place and we change the basis vector locations, you should be able to see now what's happening is based off of the first qubit right here, the leftmost qubit. Actually, this is the second qubit if it's the Q1, Q0 system, which is big Indian, by the way. Based on this leftmost qubit, this is the target qubit. This is the control qubit, and this is the target qubit right here. So if this is a 1, this becomes a 1 as well, which is why this is like this. And then if this is a 1, this one flips, right? And the X gate is applied to the second qubit if the first qubit is a 1. You can see it doesn't affect the prior ones right here. So that should remind you of C naught, where based off of the first qubit, which is the control qubit, it modifies the second qubit. Okay, so that's kind of how you can use the matrices to figure out what operation is being applied and how you can connect the operation with the matrix representation, because you should have a great understanding of like the matrix, this basis vector breakdown, and the geometric representation of the block sphere to maximize your chances of understanding it correctly in case one of them fails, because there can be some really complicated examples and you don't want to be short on like one of the tools you can use if that happens. One thing to note, the matrix size, which is always n by n, it's always square. This will be determined by the number of qubits. So if there is 1 qubit, it's 2 by 2. If there's 2 qubits, it's 4 by 4. If it's 3 qubits, it's 8 by 8. So the pattern is 2 to the n, where n is the number of qubits, or I'll do m. 2 to the m, where m is the number of qubits, is going to give you your n by n representation for the matrix size. So if it's a 3 qubit system, it'll be 8 by 8. Okay. Let's get rid of this because I jumped the gun a lot on some of the gates, but I did want to show you how the matrix representation works. So that was the X gate. It's the quantum equivalent of the inverter on the classical domain. This top left example right here, It's the equivalent of that in the classical domain. Okay. And we talked about the vector representation already. So alpha 1, this is the probability amplitude. Remember, alpha 1 squared will be the actual probability of the qubit being measured in ket 0. Okay. Now we will look at the Z gate, which is called the phase flip gate. So the Z gate is very similar to the X gate, but instead what you do is you rotate around the Z-axis instead of the X-axis. So we'll make the block sphere again. That is tiny. So we'll put Z, X, Y, and now Z is actually rotating around. So the plane that is perpendicular is the XY plane. And we will rotate around the Z-axis, again, clockwise visually to us, but really it is counterclockwise. So for a bit that starts in the plus position right here, this is a plus, it will rotate like this until this position, so it's a minus. And if it's a minus, it rotates pi degrees this way, so it becomes a plus. So that's the way to think about the Z gate. The matrix representation is 1, 0, 0, minus 1. To confirm it's unitary, remember what does unitary mean? It means the matrix times the Hermitian conjugate transpose is going to be equal to the identity matrix. So if you multiply if you take the conjugate of this, it's the exact same thing. And if you take the transpose, it's the exact same thing. So if you multiply this matrix by itself, it equals the identity matrix. Okay. And it just so happens that the X gate, the Z gate, the Y gate, and the Hadamard gate, and I think one more gate, but I don't remember which one, they're all self-reversible, which means the matrix is equal to its inverse. That doesn't necessarily have to be true. So for some matrices, the Hermitian transpose of the matrix is going to be different from its actual inverse. No, it is equal to its inverse. It's going to be different from U itself, right? So the Hermitian transpose is always equal to the inverse when it's unitary, but it doesn't have to be equal to the matrix itself. U does not have to be equal to U inverse all the time. So in these cases, the Pauli gates, it is true that U equals U inverse, but for some other gates, that's not true. So that should not be the test. The test to see whether it's unitary or not should be that U transpose is equal to U inverse. Or U transpose times U equals the inverse, because U inverse U equals the inverse, right? Okay. So that's the Z gate. The Y gate we didn't go over in the lectures. It's the same thing though. I mean, just hold XZ as the fixed plane and then rotate around the Y axis. Okay, now the next gate is the most important gate we use at the start of all quantum algorithms, which is the Hadamard gate. And the Hadamard gate on the block sphere is not as simple of a representation as you think. So we always talk about the Hadamard gate. For example, when we start at ket 0, the Hadamard gate creates superposition between 0 and 1 and takes you to this spot right here, the plus. But it's not the case that the Hadamard gate is equivalent to just a rotation this way, and it acts differently depending on what the starting vector set is. So rather than using the block sphere for Hadamard, it's a lot easier to use the unitary matrix representation, which is what we're going to try and do. Okay, so we do know it maps ket 0 to the plus state, and we know it maps ket 1 to the minus state. And Hadamard is also itself inverse. So if you apply Hadamard again, you will get back the original input. So this will be back to ket 1. Okay. Let us look at the Hadamard matrix representation now. So the Hadamard matrix representation is 1 over square root of 2 times 1, 1, 1, minus 1. And you can multiply it by itself to get back the identity matrix, or its conjugate transpose, which is the exact same thing as itself, because there are no complex terms here and the minus signs are in the corners. But let's see its effect on multiplying by the basis state vectors. So for alpha 0 and alpha 1, which are captured right here, we get, so for the first entry, it's going to be 1 times alpha 0 plus 1 times alpha 1 divided by square root of 2. So that's alpha 0 plus alpha 1 over square root of 2. And for the second one, it's going to become alpha 0 minus alpha 1 over square root of 2. And this is, or this should look familiar a little bit, but let's write it out some more. So that's alpha 0 plus alpha 1 over square root of 2 times ket 0 plus alpha 0 minus alpha 1 over square root of 2 times ket 1. So I edited out an incorrect portion and jumping back to this. So this is the expanded representation of the original basis vector representation. So what we're going to do now is take as example, so ket 0, if you apply Hadamard to it, what was ket 0 originally? It was alpha 0 equals 1 and alpha 1 equals 0, right, to get ket 0. So now if you apply the Hadamard transformation, we get 1 plus, and I'm using this formula right here, we get 1 plus 0 over square root of 2 times ket 0 plus 1 minus 0 over square root of 2 times ket 1. And that simplifies to 1 over square root of 2 times ket 0 plus ket 1, which is exactly equal to the plus state. And similarly, if you started with ket 1, then this 0 and 1s would be swapped here and you would get a minus. So we get 1 over square root of 2 times ket 0 minus ket 1, which is equal to the minus state. So you can kind of see how these vectors get taken to each other by setting the probability amplitudes equal to the original starting qubit state and then seeing how it ends up in a different state. And we say that Hadamard creates superposition from not having superposition, and it is used at the start of every quantum algorithm, so it is pretty important. Okay, so as an overview of the single qubit gates, the ones that are self-invertible are the identity matrix, which is I, the poly X, poly Y, poly Z, and the Hadamard. These are all self-invertible. In general, you can recognize that every single gate is a rotation on the Bloch sphere, or any single qubit gate is a rotation along the Bloch sphere by some or on some axis by some angle theta. So you can generally write it as r, what axis, and then the amount. So if we rotate around the x-axis pi, that's just equal to the x gate. And if we did rx by pi over 2 times, that's also the x gate. Okay. Now, let us look at gate sequences. So remember when we're applying a sequence of gates, and this is going to be a linear algebra thing. So if we start with some input right here, and we apply U1, then we apply U2, and then we apply U3 to get our output. The order you apply the gates is going to be U1 times the probability amplitude vector first. Then you're going to left multiply this result by U2, and then you're going to left multiply this result by U3. So you start from the inside, you multiply these two together, you're going to get another vector, and then you're going to multiply U2 by that vector, you're going to get another vector, and then you're going to multiply U3 by that vector, and you're going to get your final vector, which is going to be equal to that right there. Okay, so now let's look at some examples of a sequence of gates. Let's do, starting from ket 0, we apply Hadamard. I'll put the H above the arrow. So we apply Hadamard to ket 0. What happens from that? We know it rotates to the block square root of the plus state. So now we have ket plus, and now we apply the Z gate to this. A rotation, so let's look at from the plus state, which is highlighted in orange on this above block sphere right here. A rotation or a Z gate operation would be you hold the XY plane flat and you rotate along the Z axis. So we're going to do exactly that. We're going to rotate to the opposite end, which is right here. And now we're in the minus state. So this becomes a minus. And if we apply Hadamard again, we get a 1 because the minus state and Hadamard applied to it takes it to a 1. Okay, so this should look familiar. The beginning result to the end result 0 to 1 is the equivalent of an X gate, but we don't know for sure is it equivalent because we haven't tested on the other input. What if it starts as a 1? Will it become a 0? And we could trace that right now, or we could just look at the matrix multiplication and see that that's correct. So if we're applying H, Z, H, this is our U1, this is our U2, this is our U3. So we're going to first start with our leftmost H right here. That's going to be our first product. We're going to do it times the ket 0 vector. So let's do the H gate as 1, 1, 1 minus 1, and 1 over square root of 2. And we're going to multiply it by ket 0, or we can just multiply it generically by alpha 0, alpha 1 as well. And then times that on the left is going to become U2, which is a Z gate. That is 1, 0, 0 minus 1. And then finally we do Hadamard again, which is 1 over square root of 2, 1, 1, 1 minus 1. I'm just going to pull out these constants right here to create 1/2. And then we don't actually have to multiply by the vector first. We can left multiply all the matrices and then multiply by the vector at the end to make the math easier for us, so we don't have to deal with messy A0, A1 terms. But let's multiply these two together. So we get 1, 0 and 1, 1 will give us a, and I'm going to move this Hadamard 1 right here so you know I'm not forgetting about that. I'm just multiplying these two together right now. So 1, 0 times 1, 1 is going to give us a 1. 1, 0 times 1, negative 1 is going to give us a 1. This is going to give us a negative 1. And then 0 minus 1 times that is going to give us a positive 1. And then this times alpha 0, alpha 1. And then we're going to multiply these two matrices together now. So we get 1/2 times this result, which is going to be 1 times 1 plus 1 times negative 1 will give us a 0. 1 times negative 1 plus, or 1 times 1 and negative 1 times 1 and negative 1 will give us a 2. This will give us a 2 as well, and this will give us a 0. And then if you apply the 1/2, you get 0, 1, 1, 0, which is exactly the equivalent of an X gate operation. That's how you can confirm it. If we wanted to test out what happens to a specific qubit and not generally what happens to A0, A1, we can just plug in A0, A1 as the thing originally and multiply it out. So here, instead of A0, A1, if we wrote this as, and we wanted to test if it was ket 1, we just write it as 0, 1, and then multiply it out by this, and then we'll get our result and confirm it works. But it's better to just left multiply all the matrices first and then multiply by the vector to really see what the product of the matrices is and see if it looks like a gate you remember. And then you can avoid messy algebra with alpha 0 and alpha 1 that way too. Okay, cool. Now we are on C naught. So this is a little more complicated than the other original gates, which were single qubit gates. Now we're working on a multi-qubit gate or a 2-qubit gate. So C naught performs the X gate on the second qubit if the first qubit is a 1. So in a 2-qubit system where we have Q1, Q0, we can apply a C naught to Q1 so that if Q0 is equal to a 1, then the X gate is applied to Q1. And usually this is denoted in this circuit diagram. And to read it, we have to figure out which one's the control and which one's the target. I mean, the one that looks like a target is the target, and then the other one's going to be control. So this is your control, X is your control, and Y is your target here. The result of a C0 is the XOR operation, and you can see that from a truth table. So if you have an X, Y, and you did C0 to it, you applied C0, so X is the control and Y is the target, then this is a 1 and this is 0, so this becomes a 1. The Y becomes a 1, like this one flips, right? So I'll write as Y prime, so this becomes a 1. 0 and 1, this stays a 1. 0 and 0 becomes a 0. 1 and 1, this will flip the Y, so it becomes a 0. So this is exactly equal to the XOR operation, right? Only in the instance where it's only one of them does it actually become a 1, in the other instance it's 0. Okay, and the matrix for C0 we went over earlier. 1 0 0 0 0 1 0 0 0 0 0 1 0 0 1 0. So this should look like two smaller matrices. This bottom smaller matrix on the right is the X gate matrix in a 1-qubit system, and the top one is the identity matrix. And that should follow on what's going on here. It doesn't modify the first qubit, and it modifies the second qubit by applying an X gate operation to it. And we already traced out with the probability amplitudes that that's the case from earlier. Okay, that is the C0 gate. There's also a swap gate. So let me get rid of this. The swap gate is implemented as 3 C0s. I'm not going to go into detail on like how it works, but you can trace out some examples and it'll make sense. Or I can actually just, I could just multiply out the matrices, but it would be 3 4x4 matrix multiplications. Okay, so I was doing the matrix product and I just looked at the lecture slide and there's just a straight up answer of what the matrix is supposed to look like. So I'm just going to copy that instead. I would do the math myself. So 0 0 1 0 0 1 0 0 0 0 0 1. If you multiply by those alpha 0, alpha 1, alpha 2, alpha 3, you're going to get alpha 0, alpha 3, alpha 2, alpha, or sorry, I mixed them up. Alpha 2, alpha 1, alpha 3. And this should look already familiar without writing it out, but like alpha 0, 0 plus alpha 2, or let's write alpha 1, 0, 1 plus alpha 2, 1, 0 plus alpha 3, 1, 1 becomes alpha 0, 0, 0 plus alpha 1, 1, 0 plus alpha 2, 0, 1 plus alpha 3, 1, 1. And you can see that it has swapped the values of the two qubits. Okay, based on the phase, the probability amplitudes. I guess the way to derive this, if you wanted to, you could just multiply out the 3 C0 matrices and you'll get this. Okay, so the next gate is the Toffoli gate, which is the controlled C0 gate. So C0 itself is the controlled knot. This is the controlled knot. And the Toffoli gate is a 3-qubit gate, which takes as, or it just looks like this. I think this is probably the easier way to describe it. Boom, boom. It takes control A, control B, and then target C. And if A and B are both true, only then does C get flipped, and it gets flipped by the X gate. So It's the same as a C naught, but it just requires one more additional input. So this is the quantum equivalent of a logical AND gate. So we have not been able to achieve an AND gate yet, but now we can achieve an AND gate using unitary matrices. And this one's actually invertible. So you can take the result from this and reconstruct what A and B were based off of that. And the unitary matrix it's the identity matrix for the 6x6 in the top left, and then the bottom 2x2, it is the X gate, and then these are all zeros. And this is an 8x8 matrix. Okay. There's also a Fredkin gate, which is just a controlled swap. So based off of the first qubit, if it's a 1, then it's going to swap the other two. I'm not going to write that one out since we didn't really use it in the class, but that's just how it works. So let's think about the analogs of the classical gates now. So we already remembered that the equivalent of the AND gate in the classical domain over here is the Toffoli gate, which is right here. And the NOT gate was the inverter. So this inverter is the same as the C naught. So it's not the same as C naught, it's the same as the X gate, which flips 0 to 1 and 1 to 0. The XOR gate was the equivalent of C naught, and the AND gate we said was Toffoli. Okay, and just remember that all of these gates in quantum are always reversible. So any system in the classical representation, I think, can be represented by a quantum system. Any like arrangement of AND gates and ORs, but it will require more qubits to do so because it needs a reversibility requirement. Okay, so now for the final thing, which is the quantum adder. Let's look at this code right here, and let's do a side-by-side view to actually trace through the example. So I'm going to delete this, and we're going to look at my quantum adder code. So here in the quantum adder, all we had to do was add 2 4-bit unsigned inputs and return a 4-bit unsigned output. So we didn't even have to carry the final flow, but doing that shouldn't be too bad. So originally, the input to this adder gives 2 qubits, or 2 sets of qubits that are in little endian order. Little endian order, and I'm going to write it out. Okay, that's not good. Little endian order is when the most significant qubit is on the right. So it's Q0, Q1, Q2, Q0, Q1, Q2, Q3, and this would be read as like 2 to the 0, or there's Q0 of 2 to the 0, there's Q1 of 2 to the first, Q2 of 2 to the third, and so on. Big endian is instead where Q3 is our least significant bit, so it'd be 2 to the 0, and then Q0 would be our 2 to the 3. Okay. And this lab feeds it in little endian. So the first thing we do is instantly swap all of that to get into big endian order, and then we apply our operation. So the way to think about this is our first 4 qubits, Q0, Q1, Q2, Q3, were these were our A input, our first integer unsigned, and our second qubit was represented by B, which is Q4, Q5, Q6, and Q7. And then I created 3 ancilla qubits. An ancilla qubit is just like a shell qubit that's used just to store intermediate results, but isn't used in the final return value, or we don't actually need to measure it. But that was Q8, Q9, and Q10 as so. Okay, so what we wanted to do was add A to B, and what I was doing was modifying B as the result of each operation and then storing any intermediate results like the carryover into C. So the first set, first 2 lines, 174 and 175, what I do is I take Q3 and Q7 And if they are both equal to 1, the controlled C0 gate, then I flip Q10. So in the instance where I'm adding 1, 0, 1, 1, and 0, 1, 1, 1, we know the result's going to give us a 0 in this first part and then carry over 1. So we should see something similar to that right here in this quantum example. So when we're doing Q3, Q7, CCX, we're checking is Q3 and Q7 both 1? In this instance, they both are 1. So I'm going to flip Q10 from 0 to 1. And Q10 starts at 0, as did all these qubits, except for the ones that are fed in. So the ancilla ones start at 0. So now Q10 is a 1. And then I look at, and I apply CX on 3 and 7. So this is the XOR. If they are both equal to 1, then I want Q7 to become a 0. Okay, so now what just happened is this is the result. This is the sum bit of the two A and B of the respective qubit on the same index. And the carry bit gets put into the C row. So Q10 contains the carry bit. If, for example, this was a 1 and a 0, then this Q7 would not flip. It would stay. Actually, no, it would flip. If it was a 1 and a 0, then Q7 would become a 1, and the other one would stay a 1, but we don't care about this top row A because that's not our final output that we're going to read. We're going to read everything in B. So we want B to contain the correct sum bit whenever we can. If it was a 0 and a 1 that we're adding, then this wouldn't have flipped and it would have stayed a 1, and then the sum bit would have been contained correctly. In this instance, there's no carry in from a previous index since this is the very first index we operate on, so we don't do any additional operations. And the sum bit is just 0 here, and then the carry bit is a 1 right here. So the carry bit is stored in Q10, the ancilla qubit, and the sum bit is stored in B. So now B is replaced with the sum bit. Okay. The next set, 176 through 179, is the next block of code that we do. So here we do CCX on 2, 6, and 9. So what does that do? First, we look at Q2 and Q6. So if Q2 and Q6 are both 1, then Q9 is going to have to carry over a bit. And then since they are both 1, we're going to write Q9 as a 1. And now we're going to look at line 177. It does the XOR between 2 and 6, and it stores the result in 6. So that was a 1 originally. Q2 was also a 1, so now this becomes a 0. And we can write that 0 down here. So that is the sum bit. So we have the correct sum bit so far, but remember now there's a carry bit that we have to take care of, and we have to write that into 6. So what we do is we do the controlled C0 between 6, 10, and 9. So we look at Q6, our sum bit, and we look at Q10, our carry bit, and we store that result in Q9, which is our next ancilla qubit for the next index. So Q9 now contains if Q6 and Q10 are both true, which is not the case because only Q10 is true and Q6 is a 0. So this call 6, 10, 9 does not flip Q9 at all. And QC.CX of 10 and 6 checks that if 10 has a carry left over, then it's going to flip 6. So now this is going to become a 1. So we have our sum bit is updated correctly as a 1. So essentially what's happening is it's using a series of OR operations and controlled C0 operations to do the sum bit first and then check if there's any carry bits left over. And if there is a carry bit, append that result to the newly stored Q6 register, which holds all the things we're eventually going to read. So we're constantly modifying it that once we move over one column to the next left column, that this Q6 is always going to be correct and Q7 is always going to be correct. And it stores the sum bit, the correct sum bit, including the carry in and carry out. Okay, so we just do that operation again and again, basically. So we do the next set of 4, and then in the very end, since we don't need to store the overflow result, we just do Q0 plus Q4, and we just do the OR operation between the two, and then we check the ancilla qubit in QA to see if there's any carryover. So that's basically how the quantum adder works, and then I just swap it at the end to convert in the right notation. There's a lot of ways to implement a quantum adder and do it with less qubits. So if you check chat and you try asking it to come up with one, it may come up with a different order. But what this one does is I think most intuitively, since I actually experimented and came up with it, so it made the most intuitive sense, even though it's not the most efficient. It basically does the sum bit and carry bit, and it stores the carry bits in these ancilla qubits, and the sum bit it replaces the b value with, and it keeps moving over to the left and computing that with the former sum bits. And one more thing to note, that like once we get to this column right here, then Q10 doesn't even matter anymore. You never see it called after that. And then once we move to this column right here, Q9 doesn't matter anymore. You never see anything with that. So yeah, I think that's the full summary of quantum adder, the gates. If there's any questions you have, just message me in Discord or leave a comment here, whatever you'd prefer.